all the testing we've done so far has been on means, and testing means makes sense, but more common in business situations is testing a proportion. Do you like this one or this one better? Do I have this year's model over last year's model? Market share, retention rate, return on investment. Hey, what am I making back on the money I've just invested? Well, that's a percentage. That's a proportion. So I'm still going to do the similar sample statistic. Our estimator, that's going to be P, which is the number of times I got what I wanted out of the number of times I did the experiment. That's my proportion. And then my test statistic is going to have a benchmark. A proportion I think should be happening. If I want to know if people prefer this year's software update, iOS, I don't know, what did they call it? 26, iOS 25 versus the previous iOS. I could say, do you approve or disapprove of the changes made to the operating system? And I could measure the percentage of approval. What is my hope? If I am Apple and I just released this software update, what am I hoping people say? So I'm hoping that this number is bigger than 50%, right? I want more people to like it than not. Well, that would be my benchmark. Oh, I'll test against 0.5. Maybe I think it should be at least 0.8. Test against that. I want 80% of the people to think we did something good. Whatever my benchmark is. And then I'll compute a test statistic. Which is the difference between the proportion we got from our sample and our benchmark divided by the standard error for a proportion. Hang on a second. Standard error. We had a formula for a standard error. What's that number? Formula for standard error. That's based off the standard deviation for a proportion. And again, I think of that like by binomials, because proportion is a binary choice, right? Yes or no. So I go back to my binomial distribution, and I ask, what was the standard deviation on a binomial distribution? That should be on your formula sheet from the last exam. If not, you can look back in chapter 7 at the formulas for that. That number. That's the uniform one. And I apologize, this was in chapter 6, not chapter 7. Binomials are the discrete. Felix? Right. Now, the difference is in the standard error is that I want to divide this by n, right? I need to divide this by the number of people in our sample. We did that with our S and our sigma for the testing of means. So when I do proportions, this turns out to be p minus pi 0 over the square root of pi 0, 1 minus pi 0 over n. Notice this time the n is in the square root, because in the standard deviation, there's already an n in the square root. I divide the whole thing. The square root part cancels in the bottom. This is my test statistic, my calculated number. For the means, we had a z-test or a t-test, depending on what. Right, and if I knew the standard deviation, I used, and if I didn't, I used t. Here, my standard deviation is based on my benchmark, which I know. So I'm going to use z here. This is a z-calculated statistic, and I'll call it the same way we did before, a z-calc. In spite of the fact that it's for a proportion, the setup from here on out is exactly the same. I need my null hypothesis. And I need to know if I'm doing a left, a two-tail, or a one-tail right. I need to know which way I'm doing this. Then I can compare my calculated z-value to my critical z-value. Or I can look up the p-value using not the t-table, but the z-table. Great, or I can do it in my technology. I can get the inverse normal distribution information that I want. And then I make the decision. Do I keep the null hypothesis or reject it? And that's based on my comparison between the calculated and the critical value, or on the size of my p-value. Advantage. Everything else is exactly the same. And that's the best part about this. All we have to do is decide whether I'm looking at a z or a t, a mean or a proportion within the z's, and then I follow the same process. Write down my hypotheses, null and alternate, check for my critical value, and test. Page 345, problem number 49. A hospital receives 3,500 syringes. To deliver insulin. Now, I don't know how many of you know this, but people who take insulin have to shoot themselves up rather frequently, and they use really, really, really thin needles. They're 30 gauge needles. For the record, earring wire is 20 gauge or 18. So it's 4 or 5 or 6 times thinner than a standard earring wire. These are very thin, which means it's very easy for them to get bent or dulled or twisted or something. And it turns out in this system, 14 of them have defects and are unusable. The hospital has a quality requirement. 99.7% of the syringes must be good. Out of this batch is the number of rejected syringes. Reason for us to not do business with this company anymore. Let's pick a significance level. At alpha equals 0.05. Or should I say we need a new supplier? Now, I don't know about you, but syringes aren't cheap. The average medically sealed autoclaved syringe runs about $1.50 a piece. We ordered 3,500 of them. That's a little over $5,000 in this shipment alone. If I need a new supplier, I'm going to be spending money with them. Somebody who's on insulin uses 2 or 3 or 4 syringes a day. So a month's supply is 100, 120. That's a lot. This is 35 people, 35 diabetics. That's it. That's all I can supply for a month. I'm making this order every month. Should I change suppliers? First question I'm going to ask is, I'm testing to make sure I have a minimum quality of syringes. So what's my null hypothesis? Well, before I even figure out left or right, why left? So what number has got to be smaller or bigger? Because I got to figure out which way I'm testing. So I can do it either way. I can do it as a right or a left. It's the words that are in the problem that I didn't write down. At least 99.7% of the syringes must be good. I didn't write down at least, but I write it that way. So if you want to do a left tail means I want to look at a number being small, right? What number am I looking for? Greater than or equal to what? No, we can do it that way, but greater than or equal to what? Which would be a right tail, wouldn't it? And if I'm doing a left tail, I need it to be 0.003, right? I'd be looking for the number of failures. I can say, oh, I need no more than 0.3% to be bad, or I need at least 99.7% to be good. I can say it either way.
You said 0.003.
Right. Because 99.7% is a proportion of 0.997. Right? So the opposite of that is 0.003. I just converted from percent to decimal. Or 0.3%. Now, if we do that, then we're doing a right tail. And I'm saying my null hypothesis is that the population proportion is bigger than or equal to 0.997. And my alternate hypothesis will be that it is less than 0.997. On the other hand, this is set for a right tail. Right? Oh, no, wait, I've written it wrong. Stop. Less than. Less than is left. Left tail. Right? Because I'd be looking for it to be less than my benchmark. If I set it up the other way, here I'm checking for how many good syringes I've got. Here I'm checking for how many bad syringes I've got. My null hypothesis will be that the proportion of bad syringes is less than or equal to 0.003. And my alternate hypothesis will be that the proportion is bigger than 0.003, and that is what tells me it's a right tail. So depending on which way we think of the numbers, 0.997 is a perfectly good setup. I just have to do it this way and check good syringes. But look at the numbers they gave me. They gave me 3,500. What letter goes with that number? Out of all the different letters we have in our formulas up above, what letter goes with that 3,500? N. Which makes this what? But if that's X, then I'm counting bad syringes, right? And that means I'm over here. If I want to do it this way, I need a number that's not sitting up there. I need to know how many good syringes we had. And that is 3,500 minus 14. So I would need a different X depending on which setting I'm in. But in both cases, I'm going to do N is 3,500. Here, X is 14. Here, X is 3486. These are good syringes. And these are bad. Make sense? Okay. I need two pieces of information. I need my calculated z-value, and then I need either a critical z-value or a p-value. But in both cases, I need to start with my calculated z. Formula for the z calculus. Z calculated, not calculus. Wrong class. You'll notice in my formula for z calculated, it says p minus pi 0, right? What's pi 0? Over there, or it's the 0.003 over here. That's my benchmark number. What's p? Right, but it's the proportion from my sample. So P is either 3486 over 3,500 or it's 14 over 3,500. So here and here, I get different P values. Now, this is what makes me crazy. P here means proportion, but then I start talking about P values in my result, right? The p-value being smaller than alpha and all that sort of crap. There's two uses of the same letter in the same problem. I hate this. I didn't write this textbook. I didn't write the entire field of statistics. I can't fix it. My apologies. Okay, our calculated proportion here is well, you've got this one. Give me this one. 0.004. And that makes this one 996. They have to add up to 1 because they're measuring the opposite sides of the same thing, aren't they? Now, I go over here and I do my calculated z. And it's 0.996 minus 0.997 over, oh, I need the formula for this, right? Square root of benchmark, 0.997, 1 minus the benchmark, 0.003, over the square root, I'm sorry, over the number, it's all in the square root. Over here, I take p minus pi 0, 0.004 minus 0.003 over benchmark 0.003 times 1 minus benchmark 0.997. Notice that the bottom fraction, the bottom of the thing in the square root for both sides is exactly the freaking same. 99.7 times 003 over 3,500. 99.7 times 003 over 3,500. It's the same number because it's measuring the same population. Sorry, the same standard error. The only difference between these two is the one on the left is negative and the one on the right is positive. That's the only difference. They're the same number. This number over here is negative 0.001 over the square root of some disgusting thing. 0.997.003 multiplied over 3,500. This one is positive 001 over the exact same thing. What do you get for either of these numbers? Since I'm going to use my normal distribution, I really only need 2 decimal places. If I'm going to use my table, I could use more if I'm going to use my technology. Jason, what do you get? I should be getting a very small number, like a 2, 3, something. Okay, the important thing to remember is the parentheses. So if I'm going to do this one, negative 0.001 divided by the square root of 0.997 times 0.003 divided by 3,500. Notice how that's all under the square root. And then I can exit the square root. If you do it in the stages, sometimes you have to say, oh, no, I want this whole number, put parentheses around that thing in the square root. I got a much smaller number than you did. I think there's an order of okay. And if you do this one over here, you'll get positive, the same number. With me so far? Okay. So now I need 2 pieces of information. This is the first one. I either need a critical z value or I need a p-value. We'll get them both, but we'll start with the z critical. This is z calculated. Now I need z critical. Well, in order to do z critical, I need one other thing that we already wrote down up above. What is my significance? Alpha. 0.05. We're doing a one-tail test or a two-tail test? One tail. So I'm going to use z 0.05. I need to know the z value that goes with the area of 0.05, which if you wrote down all of the shortcut numbers you already have, otherwise we need to find the 0.05 on the table. Jason, you were nodding. You have that one written down? Now, since we're on the negative side, I'm going to use negative 1.645 because we're doing a left tail for this one. Over here, though, I'm doing a right tail, so the z critical is positive 1.645. It depends on which tail we're doing. If I want the left tail, I need to be on the negative side. If I want the right tail, it's the positive side. But it's the same number, same areas in the left side or the right side. Do I reject my null hypothesis or do I keep it? Sorry, do I reject or do I fail to reject? None of what I'm doing is affirmative in any fashion. It's all based on no, or, well, not no, but. I fail to reject it. I accept it because I reject when the absolute value of my calculated number is bigger than the absolute value of my critical number. And that's not what happened here. So I fail to reject. Which means what in terms of these syringes from this company? The company itself is good. This batch was not great because it was 99.6% good instead of 99.7, but it's not far enough out of outrageous that I can say, no, you guys fucked up and we're leaving you. P-value. How would I get a p-value instead of doing the critical value? I have to find the area. Right. I have to use the z table for 1.0817. And in this case, I would be asking what is the chance that z is less than negative 1.0817? Over here, I would be asking what is the chance that z is bigger than 1.0817? Now, I don't have 4 decimal places on my table, so I'm going to use 1.08. But if I go to 1.08, negative 1.0012345678. I get 0.1401. Now, that's an area, right? Remember, this is a left tail. I reject if the area I get is smaller than my significance. My significance was 5%. Did we get a number smaller than 5%? I got 14%. Oh, that's not smaller. No rejection. Which is the same result we got with the critical. Good, I get the same result both times. If I up once, I don't want to up again. Over here, if I go to 1.08 on my table, I'm in table C2. That's from the left. This is from the right, isn't it? So I'm going to have to do 1 minus. So if I go on table C2 to find 1.08, what's my value for 1.08? Wonderful. But it's 0.8599 being subtracted from 1, right? 1 minus 0.8599, which by the way is exactly 0.1401. But that's a right tail. So I'm thinking about the area up here, and I want the area to be less than 5%, and it's not. Fail to reject. Hospitals do inspections on incoming merchandise. And if they notice that the number of defects is too high, they throw out the entire shipment. I would have wasted $5,000. I would have burned it. It's medical waste. You only dispose of medical waste in the incinerator. I would have literally thrown these syringes in the trash. But this shows I didn't have to. These are okay enough. It's not that this particular shipment was disastrous, but overall, it's not a huge problem. So a type 1 error. Type 1 error would mean my null hypothesis is true, but I reject it anyway. I waste the syringes. I could run out. My diabetics could go without syringes and therefore be unable to give themselves insulin, go into sugar shock, and this is a bad thing. People twitch from hyperglycemia. It's a horrible situation. A type 2 error. Type 2 error is my null hypothesis was false, but I accepted it. That means we should have rejected it. Too many of the syringes were bad. People go to use them and they don't get the right amount of insulin. Maybe there's a blockage inside. Maybe it's bent. Maybe they injure themselves. All of these things are bad. So the real question is, was our sensitivity in the right place? Our significance? Should we have run with 5%? Should we have run with 10%? Should we have run with two tail and done a 2.5% or a 1%? Questions? Yes. And it turns out that almost all the time, alpha is 0.05. As much as I think that is weird, it has seemed to become a standard in social sciences, in lab sciences, in medical science, that if you say your p-value is 0.05, your significance is 0.05, you're good. I don't understand that. I don't make the rules. This is a consequence of the regulatory environment. Somebody up in the FDA decided that was good enough. Somebody in the federal government said, this is what we're going to insist on. Your testing has to show a p-value less than 0.05. Okay. What happens though is that means that experimental medical trials like this happen all the time. And you get an answer and then you're like, well, is it good enough for me to say, I'm going to continue with this, or I'm going to reject this treatment because of whatever else is going on? A lot of this is based on an assumption that I didn't check in this problem, but I should. I used Z. What distribution does Z go with? Back when we were doing the probability stuff, we talked about distribution functions. And we used the Z-scores to standardize data for what distribution? I'm doing Z versus T, there are only two options, right? The T test goes with my student stuff, right? And that was his Gossett's original table work. And then Z goes with what other picture? Z goes with this picture. What curve is that? The normal curve. I didn't check if this was normal. Wait a minute. How do I know if this is good enough to be normal? Well, this is a yes, no, right? This is a binomial. They're either good syringes or they aren't. We said we had to have a certain number of successes and a certain number of failures. What was the minimum number I needed for each? I needed 10. Well, literally, I actually have both the numbers I need. I need to know that X is bigger than or equal to 10, and I need to know that N minus X is bigger than or equal to 10. And we happen to have both of those numbers. What were the two numbers we came up with for X and N minus X? 14 and 3,000, which is definitely a lot bigger than 10, right? But even if I didn't know that, even if I didn't know what those numbers were, I could look at the benchmark. My benchmark was 0.003, right? And how many syringes did we get in our pile? What is 0.003 times 3,500? Which is bigger than 10, even if it is just barely bigger than 10. So my normality assumptions are acceptable in this case. I would expect, if my benchmark were true, to have more than 10 successes and more than 10 failures. Questions? This was our benchmark, though. Even if I didn't have these numbers, we used our benchmark and say, oh, I want to use 0.003, or I could use 0.997, right? And both of those numbers would be bigger than 10. As long as both of them are bigger than 10. That's what I want. When my p-value is small, I will reject. When my p-value is big, I'm failing to reject. When I use a two-tail test, because this problem, we either looked at a left tail or a right tail, we didn't look at a two-tail. When I do a two-tail, notice what it shows in that picture. It shows alpha over 2 there. Alpha over 2 there. So that 0.05 would be 2.5% down here and 2.5% up here, which means when I go to compute the p-value, I'll compute one of them. I have to multiply by 2 for both tails. Whenever I do a two-tail test, my p-value gets multiplied by 2. For the same level of significance, a two-tail test is always harder to reject than a one-tail test is. Which means if you reject in a two-tail, you're guaranteed to reject in either one-tail. Again, in the statistics menu of the graphing calculator, I can, under the test file, there's our z-test, there's our t-test at the top, right? But those are for means. There's a proportion z-test, option number 5. You'll notice there's a bunch of these that have 1s in front of them. There's a bunch that have 2s. The hell's the 2 part? Later. But if I want a 1 proportion z-test, that's option number 5 here. My proportion was 0.004. Oh no, they're using that for pi 0, 0.003. Well, no, that's the pi 0, right? P is what comes out. The p-value that I'm talking about multiplying by 2 is the one that comes out. It's this p-value here.
Oh, okay.
It's what drives me crazy when I'm doing proportions. I use the same letter twice. So 0.003, there were 14 out of 3,500. And if I'm doing 0.03, then I'm doing left. Yes? If I was doing 0.997, I'd be doing right. Said that now twice. My brain says, no, that's backwards. I want it to be at least 0.997. That means the bad stuff is to the left. If I'm doing 0.003, I want the bad stuff to be to the right. I want a right test. Calculate. We came up with 0.1401, right? They use more decimals, they get 0.1396. But that's the same answer. And see how they put the little hat on the P for the 0.04? 04? That's how they get away with using P 2 different ways. They put a little hat on it to say, this is the one you have in your proportion, as opposed to the pi 0 in the book. If it were up to me, I'd change it all to S's. But that'd screw with everybody. Questions? We accepted this batch of syringes. We decided this was not bad enough to call the company and say, guys, that we're done with you. So that's a matter of practical significance as well as statistical significance. One of the questions is always, does this actually mean something? Is this useful information? Problem 51, page 346, asks me about a call center and call guidelines for customer service reps. For orders. All telephone orders should be completed within 2 minutes. Well, nowadays, I think we're doing this all online, so there are very few operators who will answer your call and take your order, but run with it for the moment. A random sample of 64 calls show 24 lasted less than or equal to 2 minutes. Okay. At least half of all telephone orders should be completed within 2 minutes. And then I took the example and only 24 of 64 were done within 2 minutes. I need a null hypothesis. The proportion of calls should be equal to 1/2, bigger than or equal to 1/2, less than or equal to 1/2. Why? At least that many, right? So more than should be. So that means the alternate hypothesis is less than, and that means we're doing right, left, 2. Which kind of tail? Less than, left. doing a left tail. The alternate hypothesis tells me which kind of test I'm doing. Now I know what kind of test I'm doing. I'm going to do the exact same thing we just did. 24 out of 64. Grab a calculator. What's 24 out of 64? They're both divisible by 8. 0.375? Hot damn. I can still do math in my head some days. I like that. Okay, so now I'd say my benchmark is 0.5, half the calls. I take 0.375 minus 0.5, divide by 0.5 times 1 minus 0.5 over 64, all in a square root. That's my computed Z. Z calculate. I know exactly the same thing I want to do. Now, it turns out that I'm going to reject my null hypothesis when all is said and done. This is another question. 37% of my calls were completed in less than 2 minutes. 50% is what I want. Is that a big enough difference that it means something? When I do the Z calculate, my Z calculate is -2. At a significance of 0.05, I'll use the standard one, I should be at 1.645 for a left tail. And I'm at 2. Means I reject. And 2 is big enough, substantially bigger than 1.645, that I think this really does mean something. I need to train you people to answer your calls and complete them faster. If only 37% of our calls are getting taken care of in 2 minutes, and we want 50%, we can fix this. I can make you all faster. I hope. Questions? If I can't prove normal, or if my sample sizes are way too small, then I need to not use a normal distribution. That means instead of doing a normal distribution, I'm going to have to do a binomial distribution. Out of 3,500, I want to know the chance that it's less than or equal to 10.5, right? So that's probability of 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and 0. And I got to, with a chance of failure of 0.003, and I got to add all that crap. If I'm not dealing with a normal population, the calculations get longer and uglier. They're not any harder. They are just far more tedious. I have to use my binomial distribution, the CDF for the binomial, because I'm adding them all up, right? From 0 up to 10. Oh, crud. This is going to get done in Excel. I'm not going to do this by hand. I'm not even if you paid me. There's no way I'll screw it up by hand. So it's just much easier to do technologically. Questions? What's the 2? There were all those tests that said 2. I took a sample out of a stash of syringes. Well, what if instead of just testing one pile of things, I'm testing 2? I want to know GPAs, freshmen versus sophomores. Is the adjustment period going to hurt your GPA more first year freshman, or is that senioritis setting in going to hurt your GPA more? Which is it? Who's got lower GPAs? First semester freshmen or 8th semester seniors? I can do that. I can test that. But then I would say, well, is this sample different enough? Are these means far enough apart for this to matter? Are the proportions far enough? I'm testing 2 populations instead of 1. And then we can ask a better question. Are the populations related to each other? I can do the same kind of testing. Exactly the same kind of testing. But now I have to figure out what my hypotheses change to. That's the next chapter, and that's where we will start on Friday. I will see you all then. Have a wonderful rest of your day. This is the end of chapter 9. So that means the homework is due Monday. See you then.